In mathematics, the Riemann hypothesis is a conjecture that the Riemann zeta function has its zeros only at the negative even integers and the complex numbers with real part 1/2. It was proposed by Bernhard Riemann, after whom it is named. The name is also used for some closely related analogues, such as the Riemann hypothesis for curves over finite fields. The Riemann hypothesis implies results about the distribution of prime numbers, along with suitable generalizations. Some mathematicians consider it the most important unresolved problem in pure mathematics. The Riemann hypothesis, along with Goldbach's conjecture, is part of Hilbert's eighth problem in David Hilbert's list of 23 unsolved problems. It is also one of the Clay Mathematics Institute's Millennium Prize problems. The Riemann zeta function. Zeta is a function whose argument s may be any complex number other than 1, and whose values are also complex. It has zeros at the negative even integers, that is, zeta equals 0 when s is one of -2, -4, -6. These are called its trivial zeros. However, the negative even integers are not the only values for which the zeta function is 0. The other ones are called non-trivial zeros. The Riemann hypothesis is concerned with the locations of these non-trivial zeros, and states that the real part of every non-trivial zero of the Riemann zeta function is 1/2. Thus, if the hypothesis is correct, all the non-trivial zeros lie on the critical line consisting of the complex numbers 1/2 plus it, where t is a real number and I is the imaginary unit. There are several non-technical books on the Riemann hypothesis, such as Derbyshire, Rockmore, Du Sautoy. The books Edwards, Patterson, Borvine al. and Mazur and Stein give mathematical introductions, while Titchmarsh, Ivak and Karatsuba and Voronin are advanced monographs. Riemann zeta function. The Riemann zeta function is defined for complex S with real part greater than 1 by the absolutely convergent infinite series Leonhard Euler showed that this series equals the Euler product where the infinite product extends over all prime numbers p, and again converges for complex S with real part greater than 1. The convergence of the Euler product shows that zeta has no zeros in this region, as none of the factors have zeros. The Riemann hypothesis discusses zeros outside the region of convergence of this series and Euler product. To make sense of the hypothesis, it is necessary to analytically continue the function to give it a definition that is valid for all complex S. This can be done by expressing it in terms of the Dirichlet eta function as follows. If the real part of S is greater than 1, then the zeta function satisfies. However, the series on the right converges not just when S is greater than 1, but more generally whenever S has positive real part. Thus, this alternative series extends the zeta function from r greater than 1 to the larger domain r greater than 0, excluding the zeros if the zeta function can be extended to these values, as well, by taking limits, giving a finite value for all values of S with positive real part except for a simple pole at S equals 1. In the strip 0 less than r less than 1 of the zeta function satisfies the functional equation. One may then define zeta for all remaining non-zero complex numbers S by assuming that this equation holds outside the strip as well, and letting zeta equal the right-hand side of the equation whenever S has non-positive real part. If S is a negative even integer, then zeta equals 0 because the factor sin vanishes. These are the trivial zeros of the zeta function. The value zeta equals -1/2 is not determined by the functional equation, but is the limiting value of zeta as S approaches 0. The functional equation also implies that the zeta function has no zeros with negative real part other than the trivial zeros. So all non-trivial zeros lie in the critical strip where S has real part between 0 and 1. History. Es ist sehr wahrscheinlich, dass alle Wurzeln real sind. higher than where allerdings ein streng Beweis zu wünschen. Ich habe das die Aufsuchung desselben nach einigen flüchtigen Vergleichen versuchen, vorläufig beeisigt gelassen. Da für den Nachsensweg meiner Untersuchung entbehrlich schien. It is very probable that all roots are real. Of course one would wish for a rigorous proof here. I have for the time being, after some fleeting vain attempts, provisionally put aside the search for this, as it appears dispensable for the next objective of my investigation, Riemann's statement of the Riemann hypothesis, from a real rather than on the critical line. Riemann's original motivation for studying the zeta function and its zeros was their occurrence in his explicit formula for the number of primes pi less than a given number x, which he published in his 1859 paper on the number of primes less than a given magnitude. The number of primes can be recovered from this function by where mu is the Mobius function. Riemann's formula is then where the sum is over the non-trivial zeros of the zeta function and where pi 0 is a slightly modified version of pi that replaces its value at its points of discontinuity by the average of its upper and lower limits. The summation in Riemann's formula is not absolutely convergent, but may be evaluated by taking the zeros row in order of the absolute value of their imaginary part. The function Li occurring in the first term is the logarithmic integral function given by the Cauchy principal value of the divergent integral. The terms Li involving the zeros of the zeta function need some care in the definition, as Li has branch points at 0 and 1, and are defined by analytic continuation in the complex variable rho in the region ρ greater than 0, i.e., they should be considered as A. The other terms also correspond to zeros. The dominant term Li comes from the pole at s equals 1, considered as a zero of multiplicity minus 1, and the remaining small terms come from the trivial zeros. For some graphs of the sums of the first few terms of this series, see Riesel and Gauss. This formula says that the zeros of the Riemann zeta function control the oscillations of primes around their expected positions. Riemann knew that the non-trivial zeros of the zeta function were symmetrically distributed about the line s equals 1/2 plus it, and he knew that all of its non-trivial zeros must lie in the range 0 re 1. He checked that a few of the zeros lay on the critical line with real part 1/2 and suggested that they all do. This is the Riemann hypothesis. The result has caught the imagination of most mathematicians because it is so unexpected, connecting two seemingly unrelated areas in mathematics, namely, number theory, which is the study of the discrete, and complex analysis, which deals with continuous processes. Consequences of the Riemann hypothesis. The practical uses of the Riemann hypothesis include many propositions known true under the Riemann hypothesis, and some that can be shown equivalent to the Riemann hypothesis. Distribution of prime numbers. Riemann's explicit formula for the number of primes less than a given number in terms of a sum over the zeros of the Riemann zeta function says that the magnitude of the oscillations of primes around their expected position is controlled by the real parts of the zeros of the zeta function. In particular, the error term in the prime number theorem is closely related to the position of the zeros. For example, the supremum of real parts of the zeros is the infimum of numbers beta such that the error is O. Von Koch proved that the Riemann hypothesis implies the best possible bound for the error of the prime number theorem. A precise version of Koch's result, due to Schoenfeld, says that the Riemann hypothesis implies. Schoenfeld also showed that the Riemann hypothesis implies where psi is Chebyshev's second function. Growth of arithmetic functions. The Riemann hypothesis implies strong bounds on the growth of many other arithmetic functions, in addition to the primes counting function above. One example involves the Mobius function mu. The statement that the equation is valid for every s with real part greater than 1/2 with the sum on the right-hand side converging is equivalent to the Riemann hypothesis. From this we can also conclude that if the Mertens function is defined by then the claim that for every positive epsilon is equivalent to the Riemann hypothesis, the determinant of the order n Redhoeffer matrix is equal to M. So the Riemann hypothesis can also be stated as a condition on the growth of these determinants. The Riemann hypothesis puts a rather tight bound on the growth of M. Since Odlyzko and Taylor disproved the slightly stronger Mertens conjecture, the Riemann hypothesis is equivalent to many other conjectures about the rate of growth of other arithmetic functions aside from mu. A typical example is Robin's theorem, which states that if sigma is the divisor function, given by then for all n greater than 5040 if and only if the Riemann hypothesis is true, where gamma is the Euler-Mastroianni constant. Another example was found by Jerome Franel, and extended by Landau. The Riemann hypothesis is equivalent to several statements showing that the terms of the Féré sequence are fairly regular. One such equivalence is as follows. If Fn is the Féré sequence of order n, beginning with 1, n and up to 1 over 1, then the claim that for all epsilon greater than 0 is equivalent to the Riemann hypothesis. Here is the number of terms in the Féré sequence of order n. For an example from group theory, if G is Landau's function given by the maximal order of elements of the symmetric group Sn of degree n, then Massias, Nicholas and Robin showed that the Riemann hypothesis is equivalent to the bound for all sufficiently large n. Lindelof hypothesis and growth of the zeta function. The Riemann hypothesis has various weaker consequences as well. One is the Lindelof hypothesis on the rate of growth of the zeta function on the critical line, which says that, for any epsilon greater than 0, as t infinity, the Riemann hypothesis also implies quite sharp bounds for the growth rate of the zeta function in other regions of the critical strip. For example, it implies that so the growth rate of zeta and its inverse would be known up to a factor of 2. Large prime gap conjecture. The prime number theorem implies that on average, the gap between the prime p and its successor is log p. However, some gaps between primes may be much larger than the average. Kramiak proved that, assuming the Riemann hypothesis, every gap is O. This is a case in which even the best bound that can be proved using the Riemann hypothesis is far weaker than what seems true. Kramer's conjecture implies that every gap is O2, which, while larger than the average gap, is far smaller than the bound implied by the Riemann hypothesis. Numerical evidence supports Kramer's conjecture. Criteria equivalent to the Riemann hypothesis. Many statements equivalent to the Riemann hypothesis have been found, though so far none of them have led to much progress in proving it. Some typical examples are as follows. The Ries criterion was given by Ries, to the effect that the bound holds for all epsilon greater than 0 if and only if the Riemann hypothesis holds. Neumann proved that the Riemann hypothesis is true if and only if the space of functions of the form where ρ is the fractional part of z, 0 theta nu 1, and is dense in the Hilbert space L2 of square integrable functions on the unit interval. Berling extended this by showing that the zeta function has no zeros with real part greater than 1, p if and only if this function space is dense in LP. Salem showed that the Riemann hypothesis is true if and only if the integral equation has no non-trivial bounded solutions for. Weyl's criterion is the statement that the positivity of a certain function is equivalent to the Riemann hypothesis. Related is Lee's criterion, a statement that the positivity of a certain sequence of numbers is equivalent to the Riemann hypothesis. Speiser proved that the Riemann hypothesis is equivalent to the statement that the derivative of zeta has no zeros in the strip, that zeta has only simple zeros on the critical line is equivalent to its derivative having no zeros on the critical line. Consequences of the generalized Riemann hypothesis. Several applications use the generalized Riemann hypothesis for Dirichlet L series or zeta functions of number fields rather than just the Riemann hypothesis. Many basic properties of the Riemann zeta function can easily be generalized to all Dirichlet L series. so it is plausible that a method that proves the Riemann hypothesis for the Riemann zeta function would also work for the generalized Riemann hypothesis for Dirichlet L functions. Several results first proved using the generalized Riemann hypothesis were later given unconditional proofs without using it, though these were usually much harder. Many of the consequences on the following list are taken from Conrad. In 1913, Grunwald showed that the generalized Riemann hypothesis implies that Gauss's list of imaginary quadratic fields with class number 1 is complete, though Baker, Stark and Heegner later gave unconditional proofs of this without using the generalized Riemann hypothesis. In 1917, Hardy and Littlewood showed that the generalized Riemann hypothesis implies a conjecture of Chebyshev which says that in some sense primes 3 mod 4 are more common than primes 1 mod 4. In 1923, Hardy and Littlewood showed that the generalized Riemann hypothesis implies a weak form of the Goldbach conjecture for odd numbers, that every sufficiently large odd number is the sum of 3 primes, though in 1937 Vinogradov gave an unconditional proof. In 1997 Deschoilas, Effinger, Taylor, and Zinoviev showed that the generalized Riemann hypothesis implies that every odd number greater than 5 is the sum of 3 primes. In 1934, Chowla showed that the generalized Riemann hypothesis implies that the first prime in the arithmetic progression a mod m is at most km2 log 2 for some fixed constant k. In 1967, Hooley showed that the generalized Riemann hypothesis implies Artin's conjecture on primitive roots. In 1973, Weinberger showed that the generalized Riemann hypothesis implies that Euler's list of ideal numbers is complete. Weinberger showed that the generalized Riemann hypothesis for the zeta functions of all algebraic number fields implies that in any number field with class number 1 is either Euclidean or an imaginary quadratic number field of discriminant -19, -43, -67, or -163. In 1976, Miller showed that the generalized Riemann hypothesis implies that one can test if a number is prime in polynomial time via the Miller test. In 2002, Manindra Grewal, Neeraj Kyle and Nitin Saxena proved this result unconditionally using the AKS primality test. Odlyzko discussed how the generalized Riemann hypothesis can be used to give sharper estimates for discriminants and class numbers of number fields. Ono and Soundarajan showed that the generalized Riemann hypothesis implies that Ramanujan's integral quadratic form x2 plus y2 plus 10z2 represents all integers that it represents locally, with exactly 18 exceptions. Excluded middle some consequences of the RH are also consequences of its negation, and are thus theorems. In the discussion of the Heck-Turing model, Heilbronn theorem, say the method of proof here is truly amazing. If the generalized Riemann hypothesis is true, then the theorem is true. If the generalized Riemann hypothesis is false, then the theorem is true. Thus, the theorem is true. Care should be taken to understand what is meant by saying the generalized Riemann hypothesis is false. One should specify exactly which class of Dirichlet series has a counterexample. Littlewoods Theorem. This concerns the sign of the error in the prime number theorem. It has been computed that pi less than Li for all x 1023, and no value of x is known for which pi greater than Li. See this table. In 1914, Littlewood proved that there are arbitrarily large values of x for which, and that there are also arbitrarily large values of x for which, thus, the difference by minus Li changes sign infinitely many times. Skewer's number is an estimate of the value of x corresponding to the first sign change. Littlewood's proof is divided into two cases. the RH is assumed false, and the RH is assumed true. Gauss's class number conjecture. This is the conjecture that there are only a finite number of imaginary quadratic fields with a given class number. One way to prove it would be to show that as the discriminant d-infinity the class number h-infinity. The following sequence of theorems involving the Riemann hypothesis is described in Eilen and Rosen 1990, pp. 358–361. Theorem: let d less than 0 be the discriminant of an imaginary quadratic number field K. Assume the generalized Riemann hypothesis for L functions of all imaginary quadratic Dirichlet characters. Then there is an absolute constant C such that theorem: if the RH is false then h greater than 1 if d is sufficiently large. Theorem: if the RH is false then h-infinity is d-infinity. Theorem: if the generalized RH is false for the L function of some imaginary quadratic Dirichlet character then h-infinity is d-infinity. In 1935, Carl Siegel later strengthened the result without using RH or GRH in any way. Growth of Euler's totient in 1983. J. L. Nicholas proved that for infinitely many n, where phi is Euler's totient function and gamma is Euler's constant. Ribbenboim remarks that the method of proof is interesting, in that the inequality is shown first under the assumption that the Riemann hypothesis is true, secondly under the contrary assumption.